Today we will be talking about the general mechanisms of action potential. The question at hand is, how do molecules from outside of the cell get inside? Generally, channels and transporters move solutes passively or actively across neuronal membranes. If the electrochemical gradient is moving in the same direction, passive transport is performed. If the electrochemical gradient is moving in the opposite direction, active transport is performed. Using ATP, the NAK pump is able to move ions against their gradient. Resting potential is measured outside of the cell. Ion channels are critical for the unique functions of the neuron. Ions are distributed across the neuronal membrane by balancing the concentration gradient with electrical gradient. Depolarization of the neuron reduces negative Shanrage while hyperpolarization increases negative Shanrage. The smaller the stimulus, the less action potential will propagate. The larger the stimulus, the more action potential will propagate. AP is dependent on sodium outside of the cell because the rising phase is caused by an influx of sodium from outside the cell into the cell. Voltage-dependent changes in sodium and calcium conductances account for action potential. Sodium inflow through the channels depolarizes the membrane. If the depolarization reaches the threshold, it triggers action potential. During action potential, depolarization opens sodium channels, while potassium channels remain closed. The cell is more positive inside than outside. During the falling phase of the action potential, sodium channels become inactivated, blocking the inflow. This allows potassium channels to open, permitting potassium outside of the cell to flow inside, making the cell negative again. Inactive sodium channels close, while potassium continues to enter the cell. Once potassium cells start to close, sodium channels become unblocked, allowing the neuron to return to resting state.